It's probably one of the first really big questions we all ask, right? You look up at that huge, amazing sky over our heads and you just wonder, why that color? It seems so basic, but the answer? Oh, it's an incredible journey through physics, light, and even how our own eyes work.
So let's do this. Let's solve one of the most common and frankly most beautiful mysteries we see every single day. We're going to play detective, break down the evidence, and by the time we're done, you'll get why the sky is blue and why we get those fiery red sunsets.
All right, to crack this case, we have to start with our number one piece of evidence, the sunlight itself. And just like in any good mystery, it's got a secret identity.
Now, sunlight looks white, maybe a little yellowish to us, right? But in reality, it's a whole rainbow of colors, all mashed together into one beam. It's carrying all of them, red, orange, yellow, green, blue, indigo, and violet, traveling together as what we see as white light. Okay, but here's the thing, and this is absolutely crucial. These colors are not all created equal. Nope, they might travel together, but each one has its own unique personality. And when they finally hit Earth's atmosphere, that's when those different personalities cause all the magic to happen.
Think of it like this. Blue and violet light, they travel in these short, choppy, high-energy waves. They're kind of like hyperactive puppies, just ready to bounce off anything and everything they meet. But red and orange light, they're the total opposite. They travel in these long, lazy, chill waves. They just want to keep going in a straight line. This difference, the wavelength, is the key to everything.
All right, so we've got our sunlight with all its different color personalities zipping towards Earth. Let's see what happens when they finally slam into our atmosphere. This, my friends, is the main event. I like to call it the Great Blue Scatter.
Now, the official fancy science name for what happens is Rayleigh Scattering. But don't let the name scare you. It's really simple. It's just what happens when light runs into particles that are way, way smaller than its own wavelength. And guess what? Our atmosphere is jam-packed with those, mostly tiny little molecules of oxygen and nitrogen.
And the effect is, well, it's dramatic. Because of their short, bouncy nature, those blue light waves get scattered by the air molecules almost 10 times more than the long, steady red light waves. Seriously, it is not even a fair fight.
So our atmosphere basically acts like a giant, invisible pinball machine. The blue light comes flying in, hits those air molecules, and just ricochets in every possible direction. Up, down, sideways. Meanwhile, that chill red light, it just plows right on through, mostly minding its own business.
So what's the end result of all this bouncing around? Well, that scattered blue light completely fills the sky. From one horizon to the other, blue light is being bounced around and beamed down to your eyes from every single direction. And that is why, no matter where you look up on a clear day, the sky looks blue.
And case closed. Right? Well, not quite. If you've been following the logic here, a very, very smart question should be popping into your head right about now.
Exactly. If shorter wavelengths scatter more, and violet's wavelength is even shorter than blue's, shouldn't we be living under a deep purple sky? That is a fantastic question, and it shows you're really getting this. The answer is super interesting.
So there are actually two big reasons for this. First off, even though more violet light is scattered, our eyes are just built to be more sensitive to blue light. It's a little quirk of human biology. And second, a good chunk of that violet light from the sun actually gets absorbed way up high in the atmosphere before it even gets a chance to scatter down where we can see it. So yeah, it's a team effort between physics and biology that gives us our classic blue sky.
So, now that we've totally nailed why the daytime sky is blue, we can use that exact same knowledge to figure out another daily wonder, those incredible colors we see at sunset.
It all comes down to the angle. See, when the sun is low on the horizon at sunset or sunrise, its light has to travel through a much, much thicker slice of the atmosphere to get to where you are. And on that super long journey, pretty much all of that bouncy blue light gets scattered away from your direct line of sight. It just gets filtered out, leaving only the tough ones to get through.
And what's left to make that long trip directly to your eyes? You got it. Only those long, steady wavelengths. The reds, the oranges, and the yellows. So here's the key idea. A red sunset isn't about adding red light to the sky. It's about subtracting almost all the blue light first.
So let's just put it all together real quick. Blue light has a short wavelength. It scatters the most, and that gives us our blue sky. Red light has a long wavelength. It scatters the least, and it's what's left over to give us a red sunset. How cool is that? Two amazing things explained by one simple principle.
So there you go. You are now an expert on Rayleigh scattering. But I'll leave you with a final thought to chew on. We've been talking about tiny air molecules, but what happens when the air is full of bigger things, like dust, or water droplets and haze, or even pollution? How do you think that changes the rules of the scattering game? Think about it the next time you look up on a not-so-clear day. Thanks for digging into this with me.